Hello, hello! The last section in Chapter 7, which is called something like A Series of Stories of Series, tells many interesting stories indeed, but I want to dwell on one of them in this video. The idea of hacking a familiar Taylor series. This is not a standard term, but I think it describes the situation pretty well. And one Taylor series I will be especially concerned with is the binomial series, which you've seen in an exercise or two, but upon which I shall lavish unexpected attention in this video. And at the end of this video, I will give a few examples of hacking the binomial series in ways that physicists and engineers are particularly fond of. So let's jump right in. The function e to the minus x squared is quite a common one in applications of mathematics, and especially in probability and statistics, because this function lies at the heart of the so-called normal distribution. And if you've had any statistics at all, you know that finding areas under the normal distribution, something like that, is just something you do all the time. If you took a course, you probably used, if you're a little older, a so-called z-table to find those areas, or you just used a computer program to do it. If it was a typical introduction to statistics, you never even mentioned the fact that this function was the core of the normal distribution. It's not quite the exact same thing, but it's built up around this. But nonetheless, it was there in everything you did under the hood. Well, anyway, if you've had some stats and some calculus, I know you've had the latter, then of course you'll recognize, oh, when we're finding those areas under the normal curve, we're really doing an integral, or at least that's what the computer program is doing. Hey, that's pretty interesting. So when I use a computer program or look something up on a table or whatever, I'm really doing something kind of like this integral, maybe from 0 to 1 or whatever it is. And that is indeed what's going on. And since you've studied integral calculus, your first thought might be, oh, I don't need the computer, I can just do the integral. But there's a problem. This function is one of those ones that does not have an elementary antiderivative. So I can't just write down, oh, the antiderivative of this is such and such, evaluate at 0 and 1, and be done. It's not that you can't find one because you're not clever enough. There isn't one. I mean, it has an antiderivative, but not an elementary antiderivative. So the fundamental theorem of calculus, which is what we normally use to evaluate definite integrals, is of no use to us. Well, then how do we come up with an area like that, or how does the computer do it? What it's actually doing is writing down a Taylor polynomial for this function and integrating that, which is easy because it's just a polynomial. And then we can use the fundamental theorem of calculus, and we end up with an approximation to this area, which you can make as good as you like, so that when your calculator gives you 9 digits, or the tables of old give you 4 or 5 digits, it will be accurate to the right number of digits. Okay, so that's pretty interesting. And you might think, oh, well, I know how to do that. If we call this function f, then I need to crank out some derivatives, and that should be easy because this is an exponential function, right? I mean, the first derivative is going to be, well, let's see, I need the chain rule. So e to the minus x squared times minus 2x. That's not so bad. And the next derivative is going to be, ooh, now I need the product rule too. That gives me this, and I can simplify that a little bit by cleaning those up like that. And then the third derivative, ooh, this is getting really ugly now. But it's okay, you don't have to do that. There's a much easier way. We're going to hack a Taylor series we already know. Namely, we already know the Taylor series for the exponential function. It's this. And we've seen that the interval of convergence for this series is from minus infinity to infinity. This covers the entire real line. So let's take this familiar series and hack it to come up with a series e to the minus x squared. Just recognize that all these x's, this is just a dummy variable. We could have written this Taylor series as a series in some other variable, like u. Or instead of e to the u, we could have had e to the red box. We just have a red box everywhere. It's just a dummy variable. It's just a placeholder. The point is, e to the anything is 1 plus that anything squared over 2 factorial, and so on and so forth. So with that in mind, I can say, whoa, well, instead of having our anything be x or u or 17 or whatever it is, let's just let our anything, the thing that goes in the red boxes, be minus x squared. And if I do that, well, on the left-hand side, I get e to the minus x squared. But over here on the right-hand side, I'm going to get that this expression is equal to 1 plus minus x squared plus minus x squared over 2 factorial plus minus x squared cubed over 3 factorial and all the way down to infinity. We can clean this stuff up a little bit algebraically, and we end up with this. And that's it. That stuff is indeed the series for e to the minus x squared. And we got it without having to take derivatives of this thing over and over and over, thank God. We just hacked what we knew already and came up with it that way. So now, to go back to that integral that we were thinking about before, if we wanted to integrate that, or at least to come up with an approximation for it, we could start by saying that it's equal to the integral of the original integrand's Taylor series. And if what we are actually after is not a perfect equation, but an approximation, as happens with those tables and computer programs, then we're going to truncate this series somewhere, say right there. And now we have a Taylor polynomial, which is approximately equal to the integrand, so their definite integrals are approximately equal. And this, being a polynomial, is trivial to integrate. There's the antiderivative, and now we just use the fundamental theorem to say that this is equal to this, which works out to about 0.747. And if you care to have your favorite computer program approximate this integral, you will find that to 3 decimal places, you actually get about 0.747. Pretty neat, but I'll show you something even more interesting. Of course, you know the series for 1 over 1 minus x. That Taylor series looks like this. It's just the geometric series, but we know that that one holds where the absolute value of x is less than 1. The interval of convergence here is from -1 to 1. Well, let's hack this series to get a new series for 1 over 1 plus x squared. I mean, this looks a lot like this one. I could even make it explicit by rewriting this like this. Of course, these expressions are equal, but now I've got it in the familiar form, 1 over 1 minus something. That's my red box, to use the silly notation I did before. If you want, you can imagine all these x's as red boxes, or you can do what most of us do and say, well, look, what I've done is where there was x here, I've just substituted minus x squared. So everywhere there's an x here, I'm just going to pop in minus x squared in its place. And when I do that, I get this. Oh, but don't forget, the original series expansion had a restriction on it because the interval of convergence was not the whole line. Absolute value of x had to be less than 1. Well, we get the restriction up here the same way. Now the absolute value of minus x squared has to be less than 1. All right, let's clean this up. When we do so, it becomes this, a nice simple looking series. Well, let's clean up the condition too. Absolute value of minus x squared. Well, obviously the negative is gone, and in fact the absolute value is redundant because x squared is always positive. Oh, wait a second, but when is x squared less than 1? Well, that happens whenever x is between -1 and 1, or as we'd normally write that, when the absolute value of x is less than 1. So that's nice, the restriction hasn't changed at all. It can in other circumstances though, as we'll see soon. But anyway, for our new series, we have this nice new Taylor expansion. Let me get rid of this intermediate stuff. Okay, there we are. Now, this function should trigger a reflex in you. It's the derivative of something you know. It's the derivative of arctangent, in fact. Hey, that's interesting. That means I can hack my hacked series to figure out a Taylor series expansion for arctangent of x without having to take any of those nasty derivatives. Because if integrating this thing gives me arctangent, well, integrating this thing gives me arctangent, except in series form. So let's carry that out. Let's say that we integrate both sides of that equation. What happens on the left? I get arctangent of x plus a constant, cries the ghost of your previous calculus teacher. And since we're doing 2 integrals, we're going to need 2 constants. Let me call that one C1. When we integrate this side, we get this stuff. Plus another constant, cries the voice again. Fine. We'll put that in too. Well, we've got our arbitrary constant of integration here and another arbitrary constant of integration over here. Let's just combine them. Subtract him over here, like that. And now look, this is just some constant. Do I really need all those symbols to capture one constant? No, let's just roll them together and call the whole thing C. And this confirms something you saw long ago in your first calculus class, that if 2 functions have the same derivative, they can only differ by a constant. Can we figure out what that constant would have to be? Sure we can. Just think of a convenient value of x, where we can evaluate it. Let's pop in 0 on both sides. If we let x be 0 here, we get arctangent of 0, which is 0, of course. And if we let x be 0 in here, we get 0 in the parentheses plus our constant. Okay, well that tells me that c has to be 0. It's the only number that I can add to 0 and still get 0. So after all that, we can just pick off this c. And now we have our series for arctangent. Very nice. We could have obtained this same series by cranking out derivatives of arctangent, of course, but that would get pretty ugly pretty quickly. So this is a much nicer way to go. And now that we have this series expansion for arctangent, I have a little treat for you. Let x be 1 in this equation. What happens on the left? We get arctangent of 1. Well, what angle has a tangent of 1? Of course, that's pi over 4. Meanwhile, substituting x equals 1 in on the right, we get this stuff. We have this alternating series that relates the sequence of odd numbers to pi. Pi shows up in the damnedest places, doesn't it? This series was a discovery of Leibniz, so his name is often associated with this fact, which seems apt having studied Leibniz's test for alternating series, and this is indeed an alternating series, and it meets the conditions of his test. All right, the fun never stops when you are hacking familiar series, so let's work with another one. The binomial series. You have seen it in a couple of exercises, but I haven't particularly emphasized it or insisted that you memorize it. That will change now. This is another one you should add to your arsenal, alongside the familiar series for sine, cosine, e to the x, and 1 over 1 minus x. The binomial series is the series for this function, the quantity 1 plus x raised to the power of alpha, where alpha is some real constant. It's this sum of these two things that makes it a binomial. Like in your algebra days of old, when you might have referred to something like this as a squared binomial. This is actually a special case of this, where alpha is 2, but it's not a very interesting case because the expansion is finite, and that will always be the case when alpha is a natural number. So the interesting examples of the binomial series will be where this exponent alpha is not a natural number. Anyway, let's begin by quickly deriving the Maclaurin expansion for this function. Quick scratch work down here. If this is our function, then its derivative is this stuff, so its second derivative is this stuff, which means that its third derivative is just this stuff. The pattern here is clear, so I'm not going to bother to write down any more derivatives. We'll need to evaluate all these functions at 0 since we are looking for the Maclaurin series, and that's particularly easy because x appears in one place and one place only in each successive derivative. And when we let that x be 0, we get 1 plus 0 is 1, and we raise it to some power, which of course still gives us 1. So all of these factors hanging off the end of our function and its derivatives will turn into 1s when we evaluate at 0. Thus, f of 0 is just going to be 1. F prime of 0, well, that becomes 1, so the value is just going to be alpha. F double prime of 0, we put 0 in here, that becomes 1, and we are left with alpha times alpha minus 1. And something similar happens here. That 0 makes this factor 1, so F triple prime of 0 is going to be alpha times alpha minus 1 times alpha minus 2, and that pattern will clearly continue. And now we have enough information to write down the binomial series. So remember how it works to write down a Taylor series. We begin with the constant term, which is just the value of the function at the place we've centered it, 0. So that's going to be 1. Then the next term has the form f prime of 0, x, but f prime of 0 is alpha. What about the quadratic term? Well, recall that that always takes the form f double prime, evaluated at 0, and divided by 2 factorial. Well, f double prime is down here, so that term of the binomial series is going to be alpha times alpha minus 1 over 2 factorial. And what about the cubic term? What is that coefficient? Well, we know that in any old Maclaurin series, that is going to be the third derivative evaluated at 0 over 3 factorial. But we have the third derivative right down here, so substituting that in, we get this stuff. And we see the pattern. That's how it continues forever. So let me get rid of my scratch work. What about the interval of convergence for this thing? For what values of x does this series converge? Looks like I'm going to need a little more scratch work after all. In keeping with the spirit of this whole video and the corresponding section in the book, I'm not writing everything up as formally as I normally might, but what do we have to do to find the interval of convergence of this thing? Well, we have to do a ratio test. And to do a ratio test, what do we need? Well, we need that term to predecessor ratio in absolute value. Well, we could write this down very carefully and say, well, the nth term is this, and the n minus 1 term is this, and we'd get a fraction of fractions and do the usual business. But in this case, there's a quicker way to jumpstart that. That term to predecessor ratio. Remember, we said that's like the thing you have to multiply one term by to get to the next term. Well, what am I doing to get, say, from the x squared term to the x cubed term? Well, I'm clearly multiplying by alpha minus 2 upstairs to make these numerators the same, and then I'm multiplying by 3 downstairs to make those denominators the same. And then, of course, I'm multiplying by a factor of x. And it's the same thing if we were going from the x cubed term to the x to the fourth term. I would need to multiply by alpha minus 3 upstairs, by 4 downstairs, and of course by x. Well, if I wanted to get from the n-1 term to the n term, what would I have to multiply by? I'd need to multiply by alpha minus n upstairs, n downstairs, and x. And now I'm going to put it in absolute value as the ratio test demands of us. If you didn't like that, of course, you can go back, write down general expressions for these, and verify that this is what you get out of it. But it's nice to think about it the way I just did it too, I think. And it saves me a lot of precious green ink. Anyway, here's our term to predecessor ratio in absolute value. What happens to it as n goes to infinity in the tail of the series? Well, this stuff just goes to 1 because alpha is a constant. That means all that's left is the x in absolute value, and we end up with this thing. So the ratio test tells me that this series is going to converge when this limit is less than 1. So to my series expansion, I will add the caveat when absolute value of x is less than 1. And you might say, hey, wait a second, what about the endpoints? And my answer to you, for the purposes of this video, is I don't really care about the endpoints. And it's also a little stickier problem than that normally is, because the convergence at the endpoints actually depends on the sign of x. But don't worry about that. Our goal in this video is to get comfortable using the binomial series and anchoring it in your head so that you remember it. Very important that its radius of convergence is 1. We're concerned about all those infinitely many points in that interval between -1 and 1. We don't particularly care about the endpoints today. All right, how do you remember this? It's actually pretty easy. We have the expected procession of factorials down below, so the only thing new you have to remember are these constants in the numerator. We start at 1, and that's also obvious because we know any Maclaurin series starts at the constant we get by evaluating the function at 0. If you evaluate this function at 0, of course you get 1 to the alpha, which is 1. So remembering the 1 is easy enough, and you can recover it in 2 seconds if you forget. And then after that, everything is governed by alpha. You get an alpha, then alpha times alpha minus 1, then alpha times alpha minus 1 times alpha minus 2, then alpha times alpha minus 1 times alpha minus 2 times alpha minus 3, with those increasing factorials to match. The first part, the linear approximation, is especially easy to remember because it's like the alpha just comes down in front of the x and that's it. And then after that, we just have that easy pattern. Oh, a quick observation. Before I mentioned something like this, 1 plus x squared, and I said that this familiar guy from Algebra 1 is a very special case of the binomial series. Well, if we wrote it out, forgetting what you learned in algebra and just using the binomial series, what would you get? Well, the first term, the constant term, is 1. Then what do we get? Oh, this comes down and I get 2x. Let's see, then what happens? Well, then I get the 2, but then I get 1 less than the 2, and I divide by that 2 factorial, and I get x squared. And then I get a 2, and then I get 1 less than that is 1, and 1 less than that is 0, and I divide by 3 factorials, and I get x cubed. And then I get the 2, and the 1, and the 0, and the minus 1, because I keep going down by 1 over 4 factorial, and x to the 4th, and so on and so forth. But there really isn't a so on and so forth, because look, I've got a factor of 0 here. That kills this entire term. But I've got that factor of 0 here, which kills that entire term. And so on and so forth, all the way to infinity. So all I really have is these 3 non-zero terms, and 2 factorial is 2, so that cancels out, leaving me with your old friend from your very first algebra course. Well, that at least should be reassuring to see a familiar result in an unfamiliar setting. All right, to continue our basic practice expanding things with the binomial series, let's look at 1 plus x to the minus 1. When we expand this with the binomial series, we get, well, let's see. The first term is always 1. What comes next? Alpha x. Well, that's when we just bring that alpha down. So that's going to be minus 1x. So this will be minus x. All right, then I add on the next term. That's the one that instead of minus 1, I'm going to get minus 1 times 1 less than that, minus 2, all over 2 factorial x squared. Then what? minus 1 times 1 less than that, which is minus 2, times 1 less than that, which is minus 3, all over 3 factorial times x cubed. And then I would get minus 1 times 1 less than that, times 1 less than that, times 1 less than that, all over 4 factorial x to the 4th, and so on and so forth. And if I simplify these coefficients, well, I've got 2 factorial, which is 2, so those will cancel, and my 2 negatives become a positive, and all of that just becomes x squared. On the next term, I've got 3 factorial downstairs, but look, I've got 3 factorial upstairs, 3 times 2 times 1. So those cancel, although I've got 3 negatives, so that gives me a negative, and all of this stuff becomes a factor of minus 1, so I just have minus x cubed. And on the next term, well, I've got 4 factorial downstairs, but I've also got 4 factorial upstairs, so those cancel out, although I do have 4 negative factors, which combine to give me a positive, so all that stuff disappears, and I'm left with plain old x to the 4th. Let's get rid of these vast spaces. That's a little better, and I think you could see from what went before how this is going to continue. Minus x to the 5th, plus x to the 6th, minus x to the 7th, plus, and so on and so forth. So now we have the Maclaurin series for this function, which we got just by expanding it as a binomial series. Oh, and just as a quick sanity check, let's hack this very quickly to show that it agrees with something we know already. Suppose everywhere I have an x in this equation, I substitute a minus x for x. What does that quick hack give me? Well, on the left, it gives me 1 minus x to the negative 1 power. And on the right, well, the 1 just sits there. But if I let this be negative x, then I've got minus minus x, so I get a plus x. Here, if I let that be negative x, well, it gets squared, so the negative doesn't matter, and I still end up with plus x squared. If I let this x be minus x, and then cube it, well, I get 3 factors of negatives, which gives me a negative, which cancels with that negative, and I get a positive. And the same thing is going to happen everywhere. The even powers stay positive, the odd powers become positive, and everything works out as expected. Because after all, what is this thing, 1 minus x to the minus 1 power? That's 1 over 1 minus x. And this was one of the first Taylor series you ever learned. Good. Always nice to see things from a few different angles. Oh, and I should have noted on this first one, since we got that with the binomial series, that's going to hold when the absolute value of x is less than 1, because that was our condition up here. So that means down here, that would hold when the absolute value of minus x is less than 1, since that has to get changed too. But of course, the absolute value of x is the same thing as the absolute value of x, so nothing has changed with respect to the radius of convergence. And we've seen that happen a couple of times now, so skeptics among you might say, well, I don't really need to deal with that, it's always going to work out the same. No, it won't. And let's go ahead and do an example where that changes right now. Let's take an expression like the cube root of 8 plus x, and let's find the Maclaurin series for this. Now, if I had proposed that back in the beginning of Chapter 7, you would say, ugh, I've got a lot of differentiating ahead of me. But actually you don't. We can just use the binomial series. And here you may be a little puzzled and say, can we? I mean, I see that's 8 plus x to the 1/3 power, and that looks pretty promising, but it's not quite in this form because of this pesky 8. Is there something I can do about that? Yes, there is. Much of the game of algebra is taking an algebraic expression and massaging it into some form that we want. I'd really like a 1 there instead of the 8. So let's just factor out an 8 from this binomial. When we do that, we're left with 1 plus x over 8 times the 8 we factored out, and all of it's raised to the power of 1/3. Let's go ahead and play the usual exponent games here to make this 8 to the 1/3 power times 1 plus x over 8 to the 1/3 power. Oh, and while we're here, 8 to the 1/3 power, that's the cube root of 8, which is, of course, 2. And let's take stock of where we are. Have we made progress? The 8's gone, and a 1 is in its place, which I like because I'm supposed to have a 1 there. But you might say, ooh, we took 1 step forward, but did we take 2 steps back? Because I had an x there, and that's what I wanted, whereas now I have an x over 8. Actually, that part is fine, because remember what we've been saying all along when we're hacking these Taylor series. This x is just a dummy variable. We could have rewritten this series putting a u everywhere an x is, or for that matter, putting a red box everywhere that an x was before. There's nothing magical about the letter x. The binomial series tells me that if I take 1 plus whatever and raise it to some power, I get 1 plus that power times whatever, plus that power times 1 less than it over 2 factorial times whatever squared, and so on and so forth. So this stuff is fine. That x over 8 can simply be my whatever. So I've got 1 plus whatever to the 1/3 power. That's exactly what the binomial series deals with. So let's bring it over here where I'll have a little more room and start expanding out. Once I've got everything in the proper form, it's easy. The first term of the binomial expansion is always 1. Then what do I get? Well, the next term looks like this. I take this exponent and multiply it by my whatever. So I get 1/3 times x over 8. Then what? Now I start getting these fractions. 1/3 times, well, 1 less than that. Well, what's 1 less than 1/3? Minus 2/3, of course. Divide by 2 factorial, and what gets multiplied over here? The square of the whatever, the red box. So the square of x over 8. And this continues on down the road. What's the next term going to be? Well, upstairs I get 1/3 times minus 2/3 times 1 less than that. Well, what's that? Well, that's minus 5/3. All of it over 3 factorial times whatever, x to the 8th in this case, cubed, and so on and so forth. Let me close those parentheses. I can, of course, clean this junk up that I have in parentheses, and when we do so, we get this sort of thing, and we can push that 2 back inside and distribute it to get this stuff. And lo and behold, we have the beginning of the Maclaurin expansion for this function. Again, with no derivatives taken at all, except the ones under the hood in the binomial series. This at least makes sense that it should begin with a 2, because we know it will begin with the value of the function when x is 0, and when x is 0 here, this all becomes 2. Ah, but I've left something out. I didn't specify where this holds. I have this series expansion, but I know that a power series doesn't necessarily converge everywhere. In fact, I got this by expanding this as a binomial series using this expansion that I know only holds when the variable, the whatever, has an absolute value of less than 1. So what does that tell me here? It tells me that this holds when absolute value of x over 8, because that was my variable, that was my whatever, that was my thing that goes in this red box. When that guy is less than 1, this power series converges. But let's write this in a more sensible form. Absolute value of a quotient is the quotient of the absolute values, and absolute value of 8 is, of course, 8. Now let's clear the fraction, multiply both sides by 8, and we get that this series expansion holds when the absolute value of x is less than 8. So a different radius of convergence now. Not 1, but 8. Let that be a warning to you. Don't forget that important condition. All right, let's do one more example of hacking the binomial series to obtain a Taylor series for a function without having to crank out lots of nasty derivatives. Our problem is going to be find the Maclaurin series for the arc cosine function. Yikes! Nobody wants to spend all day taking deeper and deeper derivatives of arc cosine. Some of you may not even remember the first derivative. You should know it. But if you've forgotten, let me remind you. The derivative of arc cosine is minus 1 over square root of 1 minus x squared. And this is actually a fine instance of why it is nice to know derivatives like that. Because when I see that, our older, wiser eyes, now that we are used to the binomial series, sees a kind of binomial series within. Because, hey, I can write that as minus 1 minus x squared to the negative 1/2 power. Well, that stuff is really close to the binomial form. The only thing that might put me off a little bit is this negative there. Well, that's no big deal. Let's just turn that into plus minus x squared, where I am suggestively using the red box instead of the more expected parentheses. And now this stuff is perfectly in that form. It's 1 plus something or other raised to some fixed power. But before I go about expanding this, you might say, wait, hold your horses. Don't forget where you are. This is an arc cosine. It's arc cosine's derivative. Well, that's fine. If I can expand arc cosine's derivative as a series, I can then integrate it, and I will have the series for arc cosine itself, at least up to a constant, because we know if two functions have the same derivative, they can differ only by a constant. This is good. Let's keep going. Let's expand this guy. Let's expand arc cosine's derivative. Naturally, I am going to need more room here. Let's keep my negative outside and do the usual thing. When I expand that as a Taylor series, using the binomial series, the first term is always 1. The next term is the exponent times the variable, the thing in the red box, which is minus x squared here. I'm not going to bother simplifying it first, both to emphasize the pattern and to minimize the chance of my making a mistake. What comes next? Well, the exponent is minus a half, and then I have to subtract 1 from that, which takes me to minus 3/2. Divide by 2 factorial, and multiply by the square of the whatever, the thing in the red box. Let's do one more term for good measure. We're going to get a fraction that begins just like the previous one, minus a half, minus 3/2, and minus 5/2, because I keep subtracting 1 each time. Now I have 3 factorial downstairs, and I'm cubing my variable, my thing in the red box, my whatever, and on it goes. And when I crunch that stuff all down, I get, as you can verify, this stuff. Naturally, I'm only getting even powers because my whatever, the thing in the box, was itself squared, and I'm taking powers of that square. So I get a squared, a 4th power, a 6th power, and so on. While I'm here, I may as well pass that negative through as well, so that we end up with this guy. So this is a Taylor series for not arc cosine, but for the derivative of arc cosine, so long as the thing in the box, minus x squared, is less than 1. Naturally, the negative doesn't matter. I can rewrite this as absolute value of x squared, take the square root of both sides, and we have that. So in this case, nothing has changed. The radius of convergence is still 1. But we don't want the series expansion for this function. We want the series expansion for arc cosine itself. So integrating both sides, we get arc cosine of x on the left. Don't forget the constant. It's okay, as we saw in that previous example where we did something like this, we can go ahead and consolidate the 2 constants of integration on one side of the equation. Anyway, arc cosine of x is going to be an antiderivative of all this stuff. Let's see, minus x minus, it's going to be 1/6 x cubed minus 3/40 x to the 5th minus 16 times 7, 70 and 42, what is that, 112? 112 x to the 7th, and so on and so forth. But yes, plus a constant. But we can actually determine the value of this constant here. How do we do it? Well, we pick a convenient value of x to evaluate both sides at. 0 would be very convenient over here because everything would disappear except for the c. So if we stuck 0 in this side, we would just get c. If we stuck 0 in this side, we would get arc cosine of 0. But what is arc cosine of 0? It is not 0. That's the angle whose cosine is 0. Think about the unit circle. That's this angle, pi over 2. So popping in 0 for x gives us pi over 2 is equal to c. So that means this constant is actually pi over 2. I'm going to go ahead and put it in the front where we usually have the constant terms for Taylor expansions. And voila, we have the Taylor series expansion for arc cosine centered at 0. Integrating does not change the radius of convergence, so that remains 1. Really nice. I think if I had asked you back in the beginning of Chapter 7 to find a 7th degree Taylor polynomial for arc cosine so that you were condemned to take the 7th derivative of arc cosine, you would have given up in frustration long before you got there. This, in contrast, was pretty straightforward, which shows the power both of hacking series in general and the power of the binomial series in particular. Very often, we can work something into a binomial form, and even if that something is only, say, the derivative of a function we're interested in, that can be good enough. All right, enough of that sort of thing. I mentioned in the very beginning I wanted to show you how Taylor series often show up as a practicing physicist or engineer might use them. Now, I am not a practicing physicist or engineer. I have only a layman's interest in any of that stuff, but no doubt many of you taking this class are interested in precisely that question, and you deserve a good answer. Typically, the way someone in those fields might use Taylor series is to replace a fairly unruly function with a Taylor series, or at least a Taylor polynomial, so that they can then go on to analyze the situation where it's more comfortable. The most common example of this that you may well have seen already in just a basic physics class is that there are many instances where the function sine x can simply be approximated by x, at least when x is small. And the reason for that is simple. This x is simply the first-order Taylor polynomial for sine x centered at 0. The graph of sine of x and the graph of x are very close to one another when x is near 0. So if you have some complicated expression in physics involving sine of x, but those values are small, like maybe you've got a pendulum and it's only moving through very small angles, then if you're dealing with some nasty equation, everywhere you have sine of x, you might be able to just replace it by x and make your analysis much, much simpler. Instead of something involving trigonometry, you've got the easiest function in the world. But for examples more complicated than that, I was feeling out of my depth, so I looked some stuff up online. And there's a great video that I want to recommend by a guy named Zach Starr, and the name of the video is Dear Calc 2 Students, This is Why You Are Learning Taylor Series. I highly recommend it. You can find it on YouTube. And his background is in engineering, so you may find his perspective quite interesting. He talks about a few things I'm not going to talk about, like series solutions for differential equations, but I do want to focus on something that he gets into at the end of his video, where he gives 3 specific physical examples of a complicated formula that comes out of physical considerations that can then be simplified by using Taylor series. And whether or not you're interested in physics and engineering, it is interesting to see how it works. Now, one thing that struck me when he's going through his examples is that he would have some particular equation, some particular function, and then he would say, and if we expand it as a Taylor series, we get, and then we would get something simpler. But the actual details of the expansion he did not do, which is of course fine. That wasn't really the purpose of his video. But what struck me was that all 3 examples he gave were ones where the Taylor series really came down specifically to hacking a binomial series. So I thought it would be worthwhile to go through his 3 examples just to see how that works. So in some sense, the rest of this video can be seen as a kind of commentary or expansion upon this one. I will try to remember to leave a link to Zach Starr's video in the notes of this one. Okay, so his first example, and this occurs about 7 minutes and 20 seconds into the video, is about the speed of sound in air. Well, according to Mr. Starr, this is usually given by the following formula. Velocity of sound in air is this junk. 331.3 plus 0.606 T sub c, where this is the temperature of the air in degrees Celsius. Ugh, those messy constants. So where does this thing come from? It's a nice simple relationship, gives you the speed of sound in air as a linear function of the temperature of the air, but how does one get it? Well, according to the video, this is just a useful approximation of a more complete formula for the velocity of sound in air, which is this thing, a much uglier expression for the same quantity, but now involving a square root. And the claim is that the simpler one follows from this. But why? And you may be saying, no, I want to know why this one. Well, if so, then you have the heart of a physicist, and I congratulate you. You'll have to talk to your physics teacher about that. But I can certainly help you see why this is a useful and simpler version of this. And I'll bet you can see it already too. It has to do with this square root, which we can think of as an exponent, a 1/2 power. Ooh, and I've got these 2 things added together, raised to that 1/2 power. This looks like a job for the binomial series. And indeed it is. So let's spell it out here. I'm going to take this first equation, which I've just repeated what's here, on faith. The nice engineer in the video is not lying to me. Assuming this holds, how can we get to that thing? Let's begin like that. Make it a 1/2 power, as I said before, and I've decided to turn the factors around just to help ease it into the form that I like, 1 plus something. Alas, I don't have a 1, but I know what to do based on examples we've seen already. Let's just factor this constant out from both terms, and we'll end up with this thing. I'm glad there's somebody who can stand working with these ugly constants, but I'm also glad that it's not me. Anyway, let's do our usual exponent magic. And now we have something really nice, because this is exactly the form we like for a binomial series. 1 plus something raised to some fixed power. Oh, and all this junk is of course just a constant, and if you crunch it down, you get 331.4. Hey, wait a second. I've got 0.4 and he ended up with a 0.3. Is this one of these weird science significant figure things? Either that or I or he botched the arithmetic somewhere. Anyway, it doesn't particularly matter for our purposes here, so I'll keep my 4. bring it down, and of course now we are going to expand that as a binomial series. When we do that, we always begin with 1, then as always we get the exponent times the whatever, the thing that goes in the box, if you want to think about it that way. So I'm going to save a little red ink this time and not write that box. Oh, what the hell, just for you. And then what do we get? We start getting fractions. Half times 1 less than that, which is minus a half, over 2 factorial, times the thing in the box, squared, and on and on and on. But if what we're aiming at here is a linearization, a linear approximation, a first-order Taylor polynomial, then all of this stuff, all those higher-order powers, we will just neglect and pretend like they don't exist. Such is the way of the physicist, the engineer, the applied mathematician, and so on. So we can say all this junk is approximately equal to 331.4 times 1 plus half of this other stuff, and we've dropped all the second and higher order terms to get a linear approximation. And if you whip out your calculator and crank all this ugly stuff out, you should end up with something like this, which is exactly, well, not quite exactly, we do have that 4-3 discrepancy, but apart from that, it is what we claimed it should be. And we could see that pretty easily thanks to our binomial series. All right, such was his first example. Let's move on to his second example, which concerned energy. And this one begins around 8 minutes into his video, for those following at home with a score. This second example begins with the familiar formula for an object's kinetic energy, 1/2 mv squared. But thanks to Mr. Einstein, we now know that energy and mass are bound together in surprising ways, so that even when an object is at rest, it has energy simply by virtue of having mass. That wouldn't show up in this classical formula, because for an object at rest, V would be 0, and so of course the kinetic energy is 0. And so if we throw in this extra term, m0 c squared, where m0 is the resting mass of the object, and c is the speed of light, then we get what Zach Starr refers to in his video as sort of the real total energy. But that sort of modifier applies because this really isn't the true formula. This is just a simplified version of it that is good enough for most purposes. Just like in our previous example about the speed of sound in air. The linear version was fine for most purposes, but the one involving the square root was the actual deeper formula. Well, in this case, this is just a simplified shadow of the real expression, which is this. Now, these two formulas agree with one another in the special case where the object is not moving, because if you put v equals 0 in either of them, they both reduce to E equals mc squared. But when v is not 0, we get different results from these two things. But the idea is that as long as the speed is relatively modest, meaning much, much lower than the speed of light, then this approximation will be very close to what you get from this. And so physicists like this one. So our job is to explain why this is so, at least when v is much less than c, the speed of light. Why does that happen? Well, you know what the answer is going to be. This comes by expanding this thing as a Taylor series. In particular, by using the binomial series. Let's go ahead and spell it out so that you can see exactly how this happens. We're going to start with this formula and rewrite it in an algebraically equivalent manner, like this. Well, we're practically there already. We've got our 1 in the right position. Negative a half is going to be my exponent. The only thing that's not quite right is that I have a minus here where I would like a plus. And we can fix that in the usual way by turning this minus into the addition of a negative. Normally I would put parentheses here, but in keeping with our custom in this video, I'll put a red box around that. In fact, let me consolidate these squares into one. That's probably a little easier to work with. Anyway, we've got our proper form, 1 plus whatever, all raised to some fixed exponent. So now we can go ahead and expand that as a binomial series. The binomial series expansion always begins with a 1, then what? The exponent times the whatever, the thing in the red box. Yes, I know that's all very ugly, and you surely have an itch to go ahead and simplify it. And don't worry, I'll do that shortly. But again, I want to emphasize the pattern of what comes out of the binomial series. So what do we get for our next term? Well, that's a fraction. And upstairs, we get the exponent minus a half times 1 less than that, which is minus 3 halves, all over 2 factorial, times the whatever, the thing in the red box squared. And the next term is, well, you get the idea already, so I'll just put ... there. And yes, let's go ahead and clean this stuff up. That looks much nicer. And now we are going to truncate this series. There is no linear term, and I don't want to just lop it off here, because then I would just be left with m0c squared, in which case I've really cut off too much, because I wouldn't have any contribution from v, the speed of the object. So we're going to cut it off here, so that speed at least makes its appearance. And everything beyond that, we are going to neglect. And again, this makes some rough and ready intuitive sense. We're assuming that v, the speed of the object, is much less than c. So that means these v over c's are very small numbers, positive but close to 0. When I square v over c, it gets smaller still. But when I take it to the 4th power, it gets really, really small. That's the square of the square. And that thing becomes so close to 0 that it's effectively killing that term. And the effect gets even more extreme the further we go out. So yes, this is part of what goes into this statement for relativistic energy. But at low speeds, it really makes itself felt so little that we can just pretend it's not even there at all. So this stuff, we could say, is approximately this stuff. And when we distribute this through, lo and behold, we get our resting energy. But when I distribute it to the second term, the c squared here cancels with the c squared here, and we're just left with half the resting mass times the square of the speed, just like we said it should be. Hallelujah! So yes, Mr. Star was correct. This is just an approximation to this guy, and it follows by writing this out as a Taylor series, and now you've seen exactly how we do that. Just rewrite this stuff and use the idea of the binomial series, and it's all very simple. And then, rather than having to deal with this, with its square root in a denominator, we have this much simpler form for low-speed energy that we can use without any real loss. Okay, and let's move on to his third example about an electric field, and this one occurs about 9 minutes and 5 seconds into his video. In this one, he poses a problem about two opposite charges, both on the x-axis, equidistant from the origin. That distance we will call a, and though one charge is positive and the other is negative, we are going to assume that the charges have the same magnitude. And the question is about what happens to the electrical field that they generate when we go far down the x-axis. How does that field behave way down there when points are experiencing the effects of these charges? Now, I don't have much room left on the page, but imagine this continues for some ways, and then somewhere down here I will put a point x. Now, if this distance is x, and this distance is a, that means this point's distance from this charge is x minus a, and its distance from this charge is x plus a. So we won't be surprised if those two quantities show up in an expression for the strength of the electric field at that point. And you may know that the force experienced by that point as a result of each individual charge varies inversely with the square of its distance from the charge, so that the strength of the electric field at x ends up like this. There are those square distances in the denominator. This is just a constant. Don't worry about it if you don't know what those particular things refer to, or if you've never studied electromagnetism. All that matters for our purposes is that we have this expression. And in one sense, it's the answer to our question. This gives us the strength of the electric field at x, but it's a little hard to make sense of. And again, don't worry about this junk. That's just a constant. Even the stuff in the brackets is a little hard to make sense of. Like if I say, all right, I've got my point here at x, what happens if I go to a point twice as far away at 2x? What's going to happen to the strength of the field there? It's not really immediately obvious. If there was just one charge, well, then it would be easy to say, because the strength of the field falls off with the inverse square of the distance. So moving x out to 2x would reduce the field strength to only a quarter of what it was before. But that's if there's just one charge. We have these two charges with opposite sign. That's what makes it a more interesting problem. And in this form, it's not quite so clear what's going on. So what can we do? Well, these guys look like they're crying out for Taylor expansions. In particular, the binomial series. Let's see what we can do. I've got my constant, and as for the stuff in the brackets, I don't want x minus a. I want something like 1 plus something. So in both cases, let's just factor out an x and see where that leaves us. If I do this in this first term, I'm going to end up with this, and when I do it in the second term, we get this. Well, let's play our exponent games like that, and the same story here. Good. Now let's factor the 1 over x squared out of both terms and bring that out. And there it is in its new home. And these are looking better. But let's get rid of the fractions by writing these as negative exponents. Okay, that's better still. And this one is good to go. It's in our perfect binomial form. It's got the matching ones. Each case, we've got 1 plus whatever raised to some fixed power. And you might say, oh, this one's not quite as nice. I need to do the little change the minus to the plus minus trick. But actually, let's not. These two things are almost identical. So once I've expanded this as a series, I can hack it to get this one. A really simple hack, just by letting x be minus x. So let's get started. I'll bring all this stuff down, and now just expand this as a series. The first term is 1, of course. What's the next one? You know by now. It's the exponent times the thing in the box, a over x. Even if I didn't write my box, there it is. Then what? Well, you know how it goes. Upstairs we have the exponent times 1 less than that, which is minus 3, all over 2 factorial times the square of the thing in the box. Then, well, the top begins the same, except we get one more factor, a minus 4. That all goes over 3 factorial, and we multiply by the cube of the thing in the box, and so on for all the rest of the terms. Fortunately, this stuff cleans up pretty nicely. This just becomes this, of course. In this term, well, we have 2 factorial downstairs, which cancels with this 2, leaving us with a 3 upstairs. The 2 negative factors cancel out, and so this whole thing just becomes 3. Something similar happens here. 3 factorial, well, that cancels with the 3 times 2 up here, leaving us with a 4, but we've got 3 minuses, so that leaves us with a negative, and that means all this becomes minus 4. Same story on this one. All this stuff cancels out except for the minuses. The 3 minuses give us 1 minus, which cancels with that minus, and that stuff shakes out to 5. Well, let's pack this all into a tighter space. Okay, that's much better. Now I need to expand this. But as I said before, look, I already have the series expansion for that second term. This first term is the same thing if we just let x be minus x. It would turn into this, which means I can take the series expansion, let x be minus x everywhere, and that will give me the series expansion for this. So let's do that. Well, we begin with the usual 1. Now for the next term, if I let x be minus x, well, that minus combines with that minus, leaving me with plus 2a over x. Over here, when I let that x be minus x, well, that doesn't make any difference because it gets squared, so that kills the negative. So I'm going to get the exact same thing over there, like that. When I let this x be minus x, well, I cube it, so I end up with a negative that comes out here and cancels with that one. It seems that in every term, I'm going to end up with a positive, plus dot dot dot. And so now I have this interesting expression in my brackets. 1 Taylor series minus another one. And now I get a lot of cancellation. 1 minus 1. 2 times a over x minus 2 times a over x. So this actually gets doubled because you're adding a negative copy. So I'll record that down here. We get 2 of that, which will give us 4 copies of a over x. Moving on to the next terms, I get this stuff minus that stuff again. So they're gone. They cancel out. Then I get 4 times this stuff minus 4 times that stuff. So I'm doubling again, and I end up with 8 times that stuff. And this pattern continues forever. We'd get cancellations on the next term, then a doubling, then cancellations, because all the terms are positive here, whereas they alternate over here. And now we have this expression. Well, guess what we're going to do? We are going to neglect all but that first term in the series expansion, which again makes physical sense. In the original setup, we said we were looking at points x that were far away. So in other words, x was much bigger than a, which means that these a over x terms are all very small, which means raising them to higher and higher powers makes them shrink away faster and faster. And while this is tiny to begin with, this is pretty unbelievably tiny, and the next one even more so, meaning all the bulk of the effect is up here. So if we neglect all that stuff, we could say that this expression is approximately equal to this stuff. And if we now multiply all this out, let's bury the 4a in the nasty constant up here and put the x with its brothers, we'll end up with this. Ah, but this is telling us something very nice. All this stuff in the parentheses, that's just a constant. What we have established is that, to a very good approximation, the strength of the electric field at a point way out there is inversely proportional to the cube of the distance of the point from the origin. Or in terms of the example I mentioned earlier, if we start with something far away and then double its distance, the strength of the field will be only 1/8 of what it was before. If we triple the distance, it'll be only 1/27 of what it was before. Now again, there were these higher order terms there that we neglected, but they really don't have any effect, which is why we neglect them. All right, so this is a nice example of how taking this expression and expanding it in this case, 2 Taylor series and simplifying gave us a form that conveys some physical insight, whereas this original one really didn't. Okay, I hope those examples gave you a deeper appreciation for the binomial series, and that you now might have a better sense for how it gets used in some applied settings. Those 3 examples all came from the binomial series, but one can certainly find examples where the Taylor series you use to simplify things come from other series as well. They tend to come from those familiar ones though: binomial, sine, cosine, exponential, 1 over 1 minus x, or sometimes maybe that log of 1 plus x, which we also saw. There is lots of other interesting stuff in that final section of Chapter 7 that I'm not touching here. Please do read it. I think you'll find it fascinating. Some of it I've touched on some of the videos, actually, but some not. And this should be the last video I make for Chapter 7. So I will see you next time in Chapter 8. Until then, good night.